Okay. Questions?
Do we have to know about free radical halogenation and like those transition states?
Do we have to know about free radical halogenation and transition states? Where did that come from?
Talked about that in the video and how that was kind of a precursor to.
We're gonna do that at the end of the semester. So you don't have to. In the old book before Top Hat, free radical halogenation came before SN1. So we're going to talk about free radical halogenation hopefully at the end of the semester. So you don't have to worry about that right now. What else? Example problem of what? SN2 example problem. Okay, so what I would ask you to do maybe on the next exam would be to say, let's write the mechanism of taking something like hydroxide and reacting it with this would be R2-bromobutane. And so can we write the complete mechanism for this SN2 reaction? Now we are going to work our way to looking at this and saying this is an SN2 reaction, but right now I've got to tell you whether it's, well, we only know SN2, so it's going to be SN2. After next Monday it'll be SN2 and SN1. And then we'll have to talk about how you determine the difference between them so that you can just look at the reaction and go, oh, that's SN1 or that's SN2. So in terms of the mechanism for this reaction, SN2 is a one-step concerted mechanism. It only has one transition state, and that's it. And so the first part of this is to write the arrows. So the OH minus takes its pair of electrons and donates it to that carbon, and we use a full-headed arrow to show the donation of that pair of electrons. Then the carbon-bromine bond has to break, or else carbon ends up with 5 bonds. So we break the carbon-bromine bond, and we give the pair of electrons to the bromine. Okay, so those two arrows are absolutely critical to show. Julia?
How do you know that it's like the carbon-bromine bond that breaks?
Because when we're doing SN2, your carbon has to have a leaving group attached. And the leaving groups right now will be halogens. Now in the book they used another kind of leaving group, which was to have an O attached to the sulfur with 2 double bonds and then an R group on that side. That also would be a good leaving group. It would actually be better than a halogen, but right now we're just going to deal with halogens. So halogens are going to be our leaving group. So that's how we know. At this point, halogens are going to be the ones that leave, whether it's chloride, bromide, or iodide. We don't do much with fluorine. Okay, so the halogen's leaving. This reaction takes place so that the OH attacks the carbon down the carbon-bromine bond. So the transition state for this reaction is going to have the OH partially bonded to the carbon, which is partially bonded to the bromine. Okay. And what I should have done is I should have written, let me write the final product here, and then we'll go back to the transition state. Now, whenever the OH, so this bromine, this carbon-bromine bond, those bonds are kind of facing this way. They're facing this way, the other 3 bonds. As the OH group comes in, they flatten out. And then after the bromine leaves, they end up like this. My arms are not going to go there. So in the final product then, the CH3 will still be up, the hydrogen will still be dashed, and the ethyl group will still be on the bold wedge, but those bonds will now point to the right instead of pointing to the left. So that's what causes the carbon to be what's called inverted. We get an inversion of configuration. And then over here we would have our Br minus. So in terms of the final product, the OH comes in and substitutes for the bromine, but now the OH is pointed to the left. And so that makes this is the final product. So what we then do is we then write the transition state. So in a diagram, in an SN2 diagram, you go from having reactants to the highest possible energy structure, which is your transition state, and then you go down to form the products. And this is an energy plot, so your energy is going up, and what's called reaction progress is on the bottom. So as you go from reactants to products, you go through a transition state, which in general chemistry you hopefully learned that the transition state is the highest energy species in that reaction. And the transition state cannot be isolated. We cannot put transition states into a bottle and study them. Okay, they're too high of energy species. The only reason I'm saying that is because when we go to SN1 reactions, there'll be intermediates, and intermediates are the valleys in this diagram. They could be put in a bottle and studied, but transition states are so high of energy you can't. So in this case, the transition state's going to be in between the reactants and the products. What are transition states? They are the structures where you're breaking and making bonds. So in this case, for an SN2 reaction, my nucleophile is going to be partially bonded to the carbon, which is partially bonded to the leaving group. And the OH attacks the carbon down the carbon halogen bond or carbon leaving group bond. Then the other bonds flatten out. So that we still end up with bold and dashed, but this now is a trigonal bipyramidal geometry. So the OH and the Br are 180 degrees away from each other. The CH3, ethyl, and hydrogen are all 120, but this is a trigonal bipyramidal geometry, is what that looks like in an SN2 reaction. And it always looks like that. So it doesn't matter. You have three groups. You have the three groups attached to the carbon. You have over here the leaving group, and over here you have the nucleophile. This is every transition state for an SN2 reaction is going to look like that. You're just going to have a different nucleophile and maybe a different leaving group. Okay, so it's always trigonal bipyramidal. Now, if you're looking at that going, that carbon has 5 bonds, it doesn't. It has 4. Because the OH and the bromine are partial bonds. So I haven't violated any rules. I haven't violated the 5 bonds to a carbon rule. It still has 4 bonds. It's just in a trigonal bipyramidal geometry. So when we look at transition states, we have dotted lines to indicate the bonds that are being formed or broken. You can think of the transition state also as the average between reactants and products. So when you look at this, you would say no OH, no OC bond, average, partial OC bond. CBr bond, no CBr bond, average, partial CBr bond. So we're averaging the bonds. We're also averaging charges. So OH minus 1, OH 0, average, delta minus. Bromine 0, bromine minus 1, average charge, delta minus on the bromine. So a transition state is also, you can also look at it as an average of the two structures, just like a resonance hybrid was the average of the resonance structures. So in this case, what's happening is the OH group is transferring its negative charge to the bromine, so that when the bromine leaves, it leaves as a -1 species. Okay. So the mechanism of this would be the arrows, the transition state, and then writing the final product. That would be the mechanism for an SN2 reaction. And I will definitely ask you to do that on the next exam. But I'll also probably give you some graded homework problems where you're writing mechanisms as well. Okay. Now, the question about the mechanism for SN2, as people did the kinetics, they found that the rate of the equation equals K times the concentration of the nucleophile to the first power times the concentration of the alkyl halide to the first power. And so that requires going back and remembering general chemistry in the fact, how do you determine rate equations? What you would do is you make a table, you would double the concentration of the nucleophile, keep the alkyl halide constant, and see what happened to the rate. You would double the concentration of the alkyl halide, keeping the nucleophile concentration the same, what happened to the rate. And what they found was when you doubled the nucleophile concentration, the rate doubled. When you doubled the alkyl halide concentration, the rate doubled. When you doubled both of them, the rate went up by a factor of 4. So that tells you then that these exponents here are wanted. What is called first order in both of those, in nucleophile and in alkyl halide. And then overall, when you add the exponents, overall that reaction would be what we would call second order, which means that in the mechanism, in the slowest step of the mechanism, two molecules are colliding. That's what a second order reaction means. And what are the two molecules that are colliding? The nucleophile and the alkyl halide. So that's where the second order comes from. A reaction that involves two molecules is called bimolecular. And so when we have SN2, we're substituting nucleophile for nucleophile, which is the SN part, nucleophilic substitution. And then the 2 means that the reaction has bimolecular, not biomolecular, bimolecular kinetics. And so that's where the 2 comes from. All that was done by measuring the rates of the reactions. Julia?
I was just going to ask if the RX was the leading group of alkyl halide.
RX is the actual alkyl, is the entire alkyl halide. And so the X would be any halogen, because that's what we're going to deal with first, is leaving groups that are halogens. We'll work our way to other molecules. They just happen, I know, because people have asked questions about problem 715, I believe, and 715 has that as a leaving group as well. So last night, it was later last night, I did go back over and record a video and post it on Piazza about the basics of acid-base, as well as the basics of a good leaving group versus a poor leaving group. Unfortunately, it took 45 minutes. So if you're looking at that, you might want to skip to the areas you need. At that point, I wasn't going to break it up. So, and we can go back over that now if you would like as well. But I did put that, and I did talk about why this is a good leaving group. It's unfortunate they decided to throw it in right now, but it's okay. So that's the mechanism, including some other stuff. So in terms of the mechanism, if I give you a reaction to do and I show the bold and dashed wedges, what's the configuration of that chiral center is going to be R. I set it up so hydrogen is behind you, bromine number 1, ethyl number 2, methyl number 3. So that molecule started in the R configuration. In the final product, what is the stereochemistry? It's going to be S. Okay, so hydrogen is 4, oxygen's 1, ethyl's 2, methyl's 3. 4 is pointing away from me. Going from 1 to 2 to 3 is counterclockwise. So this is the inversion of configuration portion of the SN2 mechanism. When people were looking at this reaction, the first thing they wanted to do was to figure out what the mechanism was. They did kinetics to basically come up with the idea that it was first order in nucleophile, first order in alkyl halide. I guess at that point you invoke what's called Occam's razor, which is that the most likely answer to a question is the simplest one, which usually works. And in this case, they said, well, if both of those are reacting in the rate determining step, there must just be one step, which is the one I drew out. And then it got to be a little bit more tedious in terms of, well, how does the OH attack? Does the OH attack from up here? Does the OH attack from here to do front side attack? Does it do back side attack? And the easiest way to determine that was to use a chiral molecule and determine whether from the front side attack the OH would go right where the bromine was, so R would stay R if it was front side attack. That's not what they found. They found that it was backside attack, so the configuration of the molecule would change, or what we call invert. So this undergoes inversion of configuration. The first thing was chiral molecule yields another chiral molecule. So the reactant rotated plane polarized light, so did the product. If it would have gone 50-50, you would have gotten 0 rotation. So that was the first step, was we got rotation. Is it retention? Is it inversion? They found out it was inversion. So that's how this is all worked out, and I don't believe it's worked out by a single person. If it was, there would be a name associated with it, and there's not. It's just SN2. What else from this? What I said in the video on, can I condense it down from 45 minutes? Sure. What specifically what specifically do we, well, let me ask a couple questions here. So if I gave you hydroxide, fluoride, chloride, iodide, it's going to go CNOF, Cl, Br, and I on my periodic table. So if I gave you these four, which of these nucleophiles is which of these do you think is the strongest? I'll give you your choice of A, B, C, or D. And if you have your cards, and I don't have, and I did bring extra cards, but if you have a card, which one would be the strongest nucleophile? Hydroxide or iodide? So which one would be the strongest nucleophile? Hydroxide, fluoride, chloride, or iodide? We'll see how we do here and then. Okay, I've got 6. Really only have 20 people here today? I mean, it is gloomy out there, but it's not so gloomy that we can't make it to class. I've got 6. I got 6 hydroxides, 4 fluorides, and 10 iodides in terms of which one is the better nucleophile. Okay. So, first of all, let's break this down. Of hydroxide and fluoride, which one is the stronger nucleophile? And here we'll revote. So your choices are A, B, and C will be don't know. Don't know how to tell. So of hydroxide versus fluoride, which one is the better nucleophile? Sorry, which one's a better nucleophile? Just hydroxide, fluoride. Hydroxide, fluoride, don't know. Okay, I got 8 A's, 4 B's, and 2 C's. So we're kind of split between A and B, which kind of tells me I need to go back over the rules. Okay, so here's the rules for determining strength of nucleophile. So what's a strong nucleophile versus a weak nucleophile, and how do we differentiate between the strong nucleophiles? Okay, rule number 1 is that strong nucleophiles have a negative charge. So strong nucleophiles are things like all of these, hydroxide, fluoride, chloride, anything with a negative charge is what we're going to consider to be a strong nucleophile. That's rule number 1. Rule number 2 is that anything that is neutral is going to be what we call a weak nucleophile. And so what is it? If you're a nucleophile, what is your characteristic? Nucleophiles are electron rich, right? That's what nucleophiles are. So what's the source of electron richness? For hydroxide, it's electron rich because its oxygen has 3 lone pairs. Now, the negative charge is a result of having those 3 lone pairs. But your richness is having lone pairs that you can donate to something else. Okay. Same thing would be true for halogen, because a halogen has 4 lone pairs. That gives it a negative charge, but the fact that it has lone pairs makes electron rich. Okay. Are there neutral molecules that have atoms that are electron rich? Yes. The first one is water. So the oxygen in water has 2 lone pairs. That water can donate its lone pairs, and so it's a nucleophile. But we're going to consider it to be a weak nucleophile because it doesn't have a negative charge. So when you have a negative charge, you're a strong nucleophile. When you're neutral, like water. And what we're going to find this semester, this year, is anytime you have HOH, for the most part, then alcohols, ROHs, do the same thing. So this alcohol is also a weak nucleophile. It has lone pairs that makes it rich, but it doesn't have a negative charge. So that's rule number 1. Strong, negative charge, weak, neutral. Now, when we get to the negative nucleophiles, how do we know that one negative nucleophile is stronger than the other? It depends. It depends on what the relationship is on the periodic table. So when you have 2 negative charges and you have a horizontal relationship with them, it turns out that we look at the periodic table and the horizontal relationship says that the nucleophile, that a strong nucleophile or a stronger nucleophile corresponds to being a stronger base. So when we have 2 atoms or 2 molecules that are related horizontally on the periodic table, the stronger nucleophile is the stronger base. So that's a direct relationship. So when I look at hydroxide versus fluoride, which one of those 2, bless you, is the stronger base? Hydroxide or fluoride? Well, this is probably the source of confusion, so that's why we have to go through and say which one is a stronger base, hydroxide or fluoride. General chemistry has been a long time away. For some of you, longer than others. Right? If you skipped a year, it's going to be a long ways away. But if you look back in your memory, you would remember that F- is one of those bases that when you react it with water, it's in an equilibrium then with HF and hydroxide. But HF, the conjugate acid, is a weak acid because it only partially dissociates in water. Right? You probably did tons of ice charts with HF. If you don't remember what an ice chart is, Google it, and then if it still doesn't come back, I don't know what to say. But HF is an acid that is in an equilibrium when it dissociates. And that means its conjugate base F- is also in an equilibrium when it reacts with water. Okay. And maybe I should just start there and say HF, when you add it to water, you get an equilibrium with the F- and H3O+. What is F-? F- is called the conjugate base of HF. HF is considered to be a weak acid because it only partially dissociates in water. What does that mean to be partially dissociated? It means you're in an equilibrium. And that's where the ice charts came in. What does it mean to be a strong acid like HCl? So when I react HCl with water, what happens? I get H3O plus and Cl minus. So strong acids are strong because they do what? They completely dissociate in water. So, and I'm going to put that in quotes because they completely dissociate. So a strong acid completely dissociates, a weak acid only partially dissociates. And this leads to something that I do a little bit differently than I think a lot of others do when we talk about acid-base chemistry. There's the inverse relationship between acid strength and conjugate base strength, right? So if I say that HCl is a strong acid, and I said, what kind of base is Cl minus? I say that Cl minus is a non-base. Right. So Cl minus, if I go and I take salt, if I take sodium chloride and I pour it into water, am I going to change the pH of the solution? No. Right. I'm not going to change the pH of the solution. Not with chloride, or bromide, or iodide. Right. So they don't react with water. They don't hydrolyze. They don't break up water into hydroxide. So a strong acid's conjugate base is a non-base. It's not a base. But what's the conjugate base of a weak acid? The conjugate base of a weak acid is a weak base. Because the definition of weak is it's involved in an equilibrium. If I drop some fluoride into water, I'm going to end up with an equilibrium between HF and hydroxide, because it will hydrolyze water in an equilibrium expression. So weak bases will react with water in equilibrium. Strong bases would be a complete deprotonation of water, and a non-base doesn't touch water. So this goes against English, right? The opposite of strong is not non. And the opposite of weak is not weak in English. But in acid-base chemistry, opposite of strong is the conjugate base or acid isn't going to do anything. And the conjugate of weak is weak because it's involved in an equilibrium. Okay. So that's how I look at the acid-base chemistry a little bit differently. And in the I'm averaging 1 every 10 years of teaching general chemistry. When I started, I taught both general and organic like every year, which means you could have taken me for 4 consecutive semesters. Wouldn't that be fun? But setting the stage for organic, that's the way I would talk about your acid-base table. I would have these completely dissociate, they're strong, their conjugate bases on the other side aren't bases. Everything in the middle that's weak has a weak conjugate base. Everything that's not an acid, its conjugate base is strong because it completely deprotonates water. So that's the terminology that's different. So that and why do I say that? This is why the video got so long, because I figured I'd throw everything in. Is because if I said which one is stronger, hydroxide or fluoride, if you recognize the fact that fluoride comes from a weak acid HF, then you would say, oh, it's a weak base. And hydroxide, of course, is a strong base because it's going to completely deprotonate water. Now, it's going to form hydroxide on the other side, but it's going to completely deprotonate water. So this would be considered, in our world, a strong base. This would be considered weak. And so creating a periodic table trend says that as you go from right to left, your basicity increases. So in this case, a C minus is the strongest base, followed by N minus, followed by O minus, followed by F minus. So basicity increases as you go from right to left. The CH, NH, OH, FH acidity increases when you go from left to right on the periodic table. So who is the stronger base here? Hydroxide. So I can compare hydroxide and fluoride based on their horizontal relationship. Now remember, what was my ultimate goal here? The ultimate goal was, who's the stronger nucleophile? The stronger nucleophile is the stronger base. So who's the stronger nucleophile here? Hydroxide. Hydroxide is both the stronger base and the stronger nucleophile. Horizontal relationships, it's based on basicity only. Okay. Again, this is why it was 45 minutes. Because you have to go back through all of this in order to get to that answer. Okay? All right. So just where were we at? What's a strong nucleophile? Number one, negative, strong, neutral, weak. Of the strong nucleophiles, if I'm comparing two, and they have a horizontal relationship, who's the stronger nucleophile? The stronger base. Okay. But when they tried this with the vertical relationship, like when they tried this with fluoride to chloride to bromide to iodide, they found out that basicity didn't predict that. It turned out that iodide was the strongest nucleophile. That iodide was stronger than fluoride. And so then it's like, okay, well, let's try some other vertical relationships. So they tried oxygen and sulfur was a stronger nucleophile than oxygen was. And so then the trend is like going down the periodic table increases the nucleophilicity. So if you have a vertical relationship, then all of a sudden, as you go down the periodic table, you're increasing your nucleophilicity, your strength of your nucleophile. And so then you have to think about, well, why is that? I mean, why does basicity dominate horizontally, but then when we go to a vertical relationship, all of a sudden it's not basicity anymore? What is it? And if you're going up and down on the periodic table, what's changing? And what's changing is the size of the atom. Right? As we go down the periodic table, the atoms or the ions get larger. Why? Because, in the periodic table we have row 1, row 2, row 3, row 4. Those are technically called principal quantum numbers, and they're shell numbers if you want to use the super old technology or super old word which is not valid anymore. The valence electrons get farther and farther away from the nucleus. So when you have your nucleus and you have your valence electrons, the farther away they get, there's more electrons in the middle, which leads to shielding. And so those valence electrons are less tightly held by the nucleus. And the ions get bigger. So what? Well, the so what is that as the ions get bigger and the valence electrons are less tightly held, they become more squishy. And squishiness is what is called polarizability. So the technical term that we use is we say as you go down the periodic table, the ions become more polarizable. They become bigger. Valence electrons are less tightly held. They become squishier. I can deform the electron clouds a little bit more easily. Everybody kind of with me, not too glazed over. Nobody's head's bounced off the table more than once. What does polarizability and squishiness have to do with anything? Well, our basic mechanism for SN2 is to have the nucleophile, you asked the question, the nucleophile's electron cloud is going to come in, the nucleophile is going to donate those electrons to carbon, but how does that actually happen? The way that happens is two orbitals overlap. And when we remember that when we had an sp3 hybrid orbital, we had the big lobe, and then we had the little tiny lobe, and we said, let's ignore the little tiny lobe until we need it. We need it. So the way that the carbon leaving group goes is the leaving group's orbital overlaps with the carbon's orbital, but then there's this little teeny tiny orbital on the other side. Now we need that orbital, because how does an SN2 reaction occur? Number one, this is the reason why it's backside, is because that nucleophile's electron cloud is going to come in and overlap with that little teeny tiny orbital of the carbon, of the sp3 hybridized carbon. And so as it does that, the orbital gets bigger, the atoms flatten out, then this leaving group leaves with its orbital, and they flip to the other side. The bonds. So it's this orbital overlap here of the little teeny tiny sp3 hybrid orbital with the nucleophile's orbital that contains the lone pair of electrons. The stronger I can make that overlap, meaning the more electron density I can put into that orbital, the stronger the bond will be as it's forming. And the stronger the bond is, what that means is that in the energy coordinate diagram, that means that the transition state will be more stable. And the more stable the transition state, the lower energy it will have. The lower energy it has, the lower the activation energy on it. So because a nucleophile is more squishy, if I can take those clouds and I can put more electron density into a smaller space, I can overlap it better with the little teeny tiny sp3 orbital. I can form a stronger bond there and lower the energy of the transition state, which will lower the activation energy, which will make things go faster. So that's why the squishiness, that's why the polarizability increases the rate of the reaction, is because it's backside attack with the nucleophile's orbital overlapping with that little teeny tiny one that we now have to invoke. So if I'm looking at a fluoride versus a chloride versus a bromide versus an iodide, the iodide being the largest is, and as I said in the video, and as I've said for the last 20-something years, iodide is a Nerf ball. Right? We still have Nerf balls, right? We have stress balls that are squishy. Okay. Whatever your squishy thing is that you can squish. We used to have those things with the little tentacles that came out. Those kinds of stress balls. When I first started teaching, a student needed 2 of those for the exam. I don't know how she wrote and squeezed the stress balls, but somehow she managed it. Managed the stress and completing the exam. Anything you want that's squishy, it's iodine squishy. Fluoride, small. I use the example golf ball. Not squishy. So the orbital for the fluorine is fixed in terms of its electron density. For iodide, I can make it more concentrated, and that's going to speed up the reaction. So what we find is that when we have vertical relationships, that as you go down the periodic table, you end up with a stronger nucleophile simply because of polarizability. Okay. So vertical, it's polarizability. Horizontal, it's basicity. And that's how we tell whether something is a strong nucleophile and whether it's stronger, is by using those 3 rules. Negative charge, horizontal basicity, vertical polarizability. And the beauty of the leaving group is, when you're looking at leaving group ability, whether something is a good leaving group or a poor leaving group, it's totally based on one thing. Leaving group ability is based on basicity. Inversely. It's inversely related to basicity. Okay. So the stronger the stronger the leaving group is as a base, the poorer it's going to be as a leaving group. The better it is, or the weaker it is as a base, the better it's going to be. And that's why, well, that leads to the paradox of iodine. Because looking at the halogens, iodine is the weakest base. It is also the most polarizable. So iodide is both the best nucleophile and the best leaving group. So if you're going to do SN2 reactions and you want them to go 100%, don't use iodide. Because what happens is you take your Cl minus and you react it with your carbon that has an iodine on it. The chlorine comes in, kicks off the iodide. You end up then substituting the chlorine for the iodide. But then when you look at the reverse reaction, all of a sudden iodide is a better nucleophile, and so what you're going to end up with is you're going to end up with an equilibrium, because iodide is both the best leaving group and the best nucleophile. So we usually avoid iodide. There's many reasons to avoid iodide in SN2 reactions. This is just one of them, the fact that it is the best leaving group as well as the best strongest nucleophile. And short of, there was one other thing that I talked about in that video, which was the idea that, if you give me a minute, when we look at any kind of HA dissociating to H plus and A minus, this principle we'll talk about over and over and over again. If I want to shift that equilibrium to the right, what should I do? Le Chatelier is not an option, because when you add more HA, you're not going to change the percentage of HA versus A minus or H plus. So what we have to do is, if I want to shift this equilibrium to the right, I want to make A minus more stable. So anything I can do to make the conjugate base more stable is going to increase the acidity of HA. Because making A minus more stable is going to push the equilibrium to the left, to the right, in this case, to the right. And I'm going to get more A minus, I'm going to get more H plus, which makes it a stronger acid as it dissociates more. But anything I can do to that A minus and make it more stable. The example I did in the video was H2SO4. This will go all the way back to the first slide. They incorporated this thing as a very good leaving group. If you write O minus with an S double bond O's in the R, that anion is going to be very stable. The best way to make the conjugate base more stable and to push the equilibrium to the right is make that conjugate base have resonance structures. Because the more resonance structures you have, the more stable the molecule. And so that's the classic way to push the equilibrium to the right to make things stronger acids, is to use something where the conjugate base has lots of resonance structures. That's not the only way, but that's the best way. Okay? So that's 45 minutes and 20. Okay? All right, if you have questions about for those of you who didn't get a Scantron form, I'm going to email you a Scantron form by email. The problems are due on Monday. If you have questions, email me, put them up on Piazza, or come see me. But if you I'm behind on Piazza questions, I will be caught up at the end of the day, unless I get flooded with them, which I will try and keep up on. But if you have questions about those, and I would go back and look at the videos on some of this would be helpful. Okay? Other than that, have a good one-day break.